So let's look at the course. What's the point of this course? What we are going to talk about at this course. Within this course, we will be attempting to answer the following questions. Two main questions we are interested to answer. As a computer engineer, all the time we are interested in kind of writing a program with the computer, solving a program, writing an algorithm, etc. So we don't look the back end and the back of the story and the theoretical stuffs of the computation. So the question is, what problems can be theoretically solved by the computer? In the ideal world, we think computer can solve everything, but it's not the case. So we need to see what problems can be theoretically solved by the computer. Not all the problems can be solved. And what problems can be efficiently solved by the problem? What problems can be efficiently. So solving a problem is one thing, and efficiently solving a problem is another thing. So that's the thing you are interested to know and answer in this course. So computability theory comes from the first question. Is concerned with exploring the limitations of computing devices. What limitation computing devices they have in solving the problems, and the problems which can be solved by them. And in terms of complexity theory, it is related to the second one. It's concerned with classifying computable problems by their inherent difficulty. So we can say which problem is more complicated, more complex than the others, and if the machine is capable of solving that problem. So that's the whole point of this course. Computability, what is the limitation of computing devices, and complexity, what is the complexity of the problem that the machine can solve it, okay? So all these things we are facing with three different things. We are facing with the languages, we are facing with the machine, and we are facing with the grammar. So we are facing with a language, we have a language. So in this course, we will see the computation can be regarded as a process of language recognition. So for a machine to compute on something, do a computation on something, language is a very important thing. So the recognition of word, and language by itself is consisted of words, okay? So the recognition of word in the language corresponds to acceptance of an input by the program. So the machine wants to do some sort of computation. For doing that, we need to have a language, and language is facing with some words. Why? Because machine should take some inputs to the program, and what are those inputs? The words, and words are part of the languages. So for computability and complexity, we need to know about the languages, type of languages, grammars, machines. So three different parts: languages, grammars, and machines, okay? Or automators. We need to talk about them. We will study a number of languages of increasing descriptive powers. See, we have been faced with different languages, with different kind of low level or high level, different kind of languages. Okay, we'll also study a number of automata, the abstract machines. You remember I said language, grammar, and machine, abstract machine, automata. This machine is not kind of a physical machine, that's kind of an abstract machine, but it is really correspond to the physical machine. I mean, we will have the same stuff in the real world, in this abstract world also. It can be used to recognize each of these languages. Some of automata, which we will study, are as powerful of any real computer, while others are less powerful. It is really similar. And to be honest, the comparison we will have in the physical world in terms of if this machine is more powerful, the other one or not, comes from that comparison in the abstract, in here, in the automatas. It is the same, yes. In automata, we have different sort of power in terms of computations. So we will see that less powerful automata are nevertheless quite useful. Very similar to physical world. If you have a computer which is less powerful, still it is useful. Or probably you cannot solve more complicated problems with them, okay? So I try, that's one technique of teaching. Owing to my more than 10 years of teaching experience, I use this technique to teach you the stuffs and make the things clear for you. I'm trying to use the similar ideas to teach you the unfamiliar ideas. Familiar ideas to go to unfamiliar ideas. Okay? We'll also study following equivalent general model of computation devices. Turing machine, that's a kind of the machines. I talked about the mathematical model of hypothetical computing machine, which can use a predefined set of rules. We have set of rules in grammar. When you are talking about the grammar, the language, and then the grammar. In the grammar, we have the rules. Rules are regulations which you convert one string to other. Okay, to determine a result from a set of input variables. Lambda calculus, a formal system in mathematical logic for expressing computation based on functions. We will go through all these things through the course. You don't need to get the point of all these things, but that's a summary of what we want to talk about in this module. It is a universal model of computation that can be used to simulate any Turing machine. Unrestricted grammars and partial recursive function. Okay, so general models of computation. These are the general models of computation. What's computability? We talk about computability. What are the limitations of computation devices? So deal with the following question. Do algorithmic solutions to problems always exist? Is it possible to find an algorithm for any problem? It is interesting. During my PhD, I was facing with this kind of question in my mind. What are the limitations of computation devices? We talked about that before in terms of computability. How can we gain insight into which problems are algorithmically solvable and which are not? So, like I said, we think everything is solvable, but it's not solvable. That's the same thing in the real life also. When we are younger, we think every problem can be solved. Like the kids, they want to make everything happen. They don't believe if something is not possible to happen. But when you get older, according to your experience, slowly you understand, no, there are things in the life that is not possible to happen. So that's the same. It's not possible algorithmically solve any kind of the problem. Are the unsolvable problems somehow related? That's a good question. For example, will function f terminate to all positive value? What's the function? We define this kind of function. We take an integer value n. If it is not 1, if it is even number, make it half, and otherwise time it by 3 plus 1, and then return. So continue until you get to n equal to 1. So that's the question. Will function f terminate for all positive value of n? If n is 2, n is not 1, okay, n is 2, make it half, 2 divided by 2 is 1, we'll jump here, n is 1, we will finish, just one go. If n is, for example, 3, n is not 1, n is not even, n is 3, so 3 by 3 is 9, plus 1 is 10, back here, at here, even, so divided 5, back here, 5 divided by 2, it's not even, so multiply, see, that's crazy. So 3 times 5 is 15, plus 1, 16, come here by 2, 8. 8 is, 16 in here, divided 8, back to here, 8 is even, divide 4, back here is even, 4 divided by 2, 2, back here, 1, finish. So for 3, you see, it happened. So that's a good question. It is computability. False conjecture. Start with any, that's called Collatz conjecture. So start with any positive integer, and then if the number is even, that's exactly what I mentioned. So we don't need to redo this. Okay, so here is the following question. In terms of complexity, that was computability. If it is possible to compute something, if that algorithm finishes, is terminated somewhere, somehow, or no, it's not terminated at all, so it's not computable. So look at the complexity. Here's with the following question. How do we compare the efficiency of different algorithms? How do you say if this algorithm is better than the other one, more efficient? The word better is kind of vague or weird word. It's not a good idea to say better, because we need to compare the things based on a specific KPIs. Okay, how do we compare the efficiency of different? How do we measure time memory requirements? That's the matter of complexity. What problems are efficiently solvable? Okay, efficiently solvable. In computation, we say what problems are solvable at all. Here we say what problems are efficiently solvable. Are these solvable problems which do not have efficient algorithms? Are there solvable problems which do not have a lot? Scientists, they are facing with this kind of problems. Mathematicians, physicians, lots of people in science, they are facing with this kind of problem. They know there are solvable problems which do not have efficient algorithm or solution for them. Or look at that, a human being knew from long time ago what is the human being artificial intelligence system. They wanted to replicate it. That was like uncomputable problem or unsolvable, inefficient solvable problem. For example, I hear they have created a similar case of the kidney, human kidney, artificial kidney, I would say, and that was the size of that was crazily big, like the size of a city or something like that. So that's the matter of this. How complex is the problem we are talking about? And are there solvable problems which do not have efficient algorithm? For example, can we efficiently determine the factor P and Q of a product P and Q? Problems. Let's look at the problem, type of the problem. We might face with a decision problem, written either yes or no, or equivalently true or false, 0 or 1. You're familiar with that. Search problems. Find an X that satisfies property P. Search problem. Optimization problem that are kind of these problems. What is the optimum solution for this problem? You search inside the space to find. For example, in my thesis, I was searching the pose of the human being in front of the camera. Based on the dimension of the pose, which was 13, I was searching inside the space of 13D dimension to find the best solution. That was a search problem. Enumeration problem. Find all X that satisfy the problem. Counting problems. Count the number of X's that satisfy property P. Right? So here you find the solutions, but you are not interested in the number of solutions, but here you are interested in the number of solutions. Optimization problem, find the X that best satisfy property. So maybe that's kind of different from here, because you might find some solution in here which satisfies, but that's not the best. And a structuring problem, transfer X to satisfy property P. How we change X to something new to satisfy the problem. Again, in computing, you're facing a lot of problems which falls in this category. The problem specification, we are still talking about problems. The problem specification comprises the characterization of all legal input to the problem, the characterization of all desired outputs as a function of the legal output. So when you are trying to describe a problem, you need to say what are the legal inputs for the problem and what are the desired output as a function of the legal input. So the problem we are facing with what could be those functions to generate those desired outputs from this legal input. Even in the real life, you can reflect it. See, you are facing with a specific problem, decision-making problem, what study you want to do, what job do you want to take? So what are the inputs? What is important for you? And what is the desired output? Okay. So some example problem here. Problem 1, input, 2 non-negative integer x and y, output, the greatest common divisor of x and y. Problem 2, input, a positive integer n, output, yes if n is prime and no if it is not. So to solve a problem, first of all, you need to know these two things, legal input and desired output. And if you know that, then you try to find the function. Like I said, in the real life, it works perfectly. In the real life, it works perfectly. this kind of character specification of the problem. What's the algorithm? Algorithm can be used to solve problems. Here we were looking for the functions. In other words, that's algorithm. An algorithm is a finite sequence of operations for solving a problem. Finite sequence of operation. If you see this input, do this operation, convert it to this, then do this operation and do lots of other stuff. Operation could be decision making, operation could be any transformation, operation could be anything. And then each operation is chosen for us from a set of well-defined operation. That's very interesting, isn't it? So you have a finite sequence of operation to solve the problem, and you have each operation is from a well-defined operation. Okay, so that's algorithm. That's the definition of algorithm. If the algorithm is executed by suitable processor on any instance of the problem, it will give rise to process that halts in a finite time, returns the answer for the problem. So that's the two different situations might happen. If you run the algorithm on any suitable processor, maybe an abstract machine or a physical machine, two things might happen. It might halt in a finite time. It is finished somewhere, returns the answer for the problem instance. That's what we are looking for. So let's look at an example algorithm. Input the positive integer n, output the sum of integer from 1 to n. Algorithm 1. Sum is equal to 0 for I from in the range of 1 to n plus 1. Before n plus 1, I mean the last one is n. So sum is the last sum plus 1 and return the sum. Or it could be another algorithm which does the same thing. Return n plus 1 times by 2, because you know summation of all the positive integer from 1 to n is n times n plus 1 divided by 2. So these are two different kinds of algorithm. Which one is more complex? Which one is better in terms of computability, etc. How can we be sure that an algorithm or program solve a problem? Okay, how can we be sure that it terminates and produces the correct output for all its legal input? For example, consider the following problem: if f of n is equal to 1, print hello world, where if is the given as given previously. This function, where was the f? F was here. This function f, which we take an integer value. If it is not 1, if it is even, make it half. If it is odd, times by 3 plus 1. So let's back to this question. So the question is here. So if f of n, you take a number and the output is 1, that means if it is terminated, print hello world. Where f is defined, like we said, is this equivalent to following? What does it mean? What does it mean? It means, does the function terminate? Does the algorithm terminate all the time? Is there a specific time you will see the function will be finished in here? The function will be finished and return n. F, when you give, for example, 10, f generates 1, and then if f is 1 here, then you print hello world. Is it similar to this one? So that's the matter of the thing we need to answer. If any algorithm is here to solve a problem, or no, it's not here to solve the problem. And then afterward, the course outlines. Let's finish this session. Let's summarize this session with this one. We are going to talk about regular languages and finite automata, regular expression, finite state automata, regular grammars, context-free languages and push-down automata, context-free grammars, derivations, ambiguity, push-down automata, context-sensitive languages and linear-bounded automata, context-sensitive grammar. You see, in all of these languages, you have the grammars and automata. So like I discussed in the beginning of this presentation, we are facing with the language, grammar, and machine. So we are facing with regular language, its grammar, and kind of the grammar. and the machine and the finite automata. We are facing with context-free language and the grammar and the machines. We are facing with the context-sensitive languages, the grammar and the machine. And general model of computation at the end. Turing machines, unrestricted grammars, practical recursive function, lambda calculus, Church-Turing thesis. In terms of computability, computability, halting problem, reducibility, complexity. We'll discuss these things. So that's the outline of the course.